Hello friends, myself Praveen Pathak. I have done my master in chemical engineering and today I am going to discuss about one of the important aspect in chemical engineering, that is mass transfer operations. Now in the mass transfer operations, there are various unit operations like distillation, crystallization, gas absorption, liquid-liquid extraction, drying, etc. And in all these operations, the basic phenomena is diffusion. And that is why we must know about the diffusion concept. So let us discuss the diffusion concept in this presentation. The contents for these presentations are concept of diffusion, role of diffusion in mass transfer, Fick's law of diffusion, steady state equimolar counter diffusion, steady state diffusion through a stagnant gas film. And the learning objective for this presentation is that the students should be able to solve the following questions like what is diffusion or define diffusion, what is the role of diffusion in mass transfer phenomena, define Fick's law or write down the equation for Fick's law, then derive the equations for steady state equimolar counter diffusion in gases, or derive the equation for steady state diffusion through a stagnant gas film. Now let us discuss what exactly the diffusion is. So from the definition point of view, it is the movement of an individual component through a mixture from a region of higher concentration to a region of lower concentration at fixed temperature and pressure with or without the help of an external force. So it is the movement of components or the molecules from high concentration region to the low concentration region at fixed temperature and pressure conditions. So the diffusion may occur with or without the external force. So diffusion may occur naturally or diffusion may occur with the help of external force, that may be a stirrer, an agitator, a driving force, or some convective currents, etc. So if the diffusion occurs naturally and there is a molecular movement, then it is called as molecular diffusion. If the diffusion occurs with the help of external force with high velocity or with high turbulence, then it is called as eddy diffusion or turbulent diffusion. So let us understand the diffusion concept with this simple example. So in this diagram or picture, you can observe there is a bromine vapor at the bottom side of this cylinder and air is present at the upper part of this cylinder. So here bromine at high concentration and bromine at low concentration or zero initially at the upper level, right? So this is the initial case, and after some time we can observe that some molecules of this bromine is diffused to the upper part in this cylinder, and after several hours these bromine vapors reach the top of the column. So there is no movement of this bromine in the third case. So it is nothing but an equilibrium condition, or when the concentration difference becomes zero. So if the delta C becomes zero, then there is no movement of molecules or the particles or the components in that area. So if there is a difference in the concentration in that region, then and then only molecular movement or the component movement will occur, and that process is called as diffusion. That is the simple concept. Now there are two types. If the diffusion occurs with the help of molecular movement, then it is called as molecular diffusion, and if it is occur with the help of external force, then it is called as AD or turbulent diffusion. So molecular diffusion is a slow process, and normally it happens in the stationary fluid and in a laminar flow condition. And turbulent diffusion is a fast process, and its mechanism is based on the turbulent flow conditions. So in the molecular diffusion, when we are talking about the molecular movement, so obviously when we compare this gas, liquid and solid, then the molecules of gases are lighter than the liquid and than the solids. So obviously the molecular movement of gases is more than the liquid and is more than the solid. And in this way, the rate of mass transfer with respect to the molecular diffusion in the gases is more than the liquid, which is more than the solid. Then the next concept is role of diffusion in mass transfer. Now we discuss about the diffusion concept, two types of diffusion, and now the role of diffusion in the mass transfer operations. So we have already discussed there are various mass transfer operations, mainly distillation, gas absorption, crystallization, drying, liquid extraction. So the diffusion may occur in one phase or in both phases. So in the distillation case, the more volatile component, that is low boiling point component, diffuses through the liquid phase to the interface. So interface means where the liquid as well as the vapor phase are occur or present. So from the interface, again this MVC is going to diffuse into the vapor phase. So MVC is diffusing through the liquid phase as well as through the vapor phase. So both phase mass transfer operation occurs with the help of this diffusion phenomena in the distillation. Now in the gas absorption, the solute gas diffuses through the gas phase to the interface and then through the liquid phase. In the crystallization, the solid solute diffuses through the mother liquor, that is liquid phase, and then to the solid phase. And in the drying operation, the moistures or the liquid water diffuses through the solid and then evaporates and then diffuses to the gas phase. In the liquid extraction process, the liquid solid is going to diffuse through the liquid phases only. So one of the liquid phases, raffinate phase, and another liquid phase is extract phase in the extraction phenomena. Then the next concept is Fick's law. So there are two Fick's laws, first law and second law. Now we are going to discuss about the first law of diffusion. So in the first law of diffusion, Adolf Fick in 1955 described the molecular diffusion in an isothermal, isobaric and binary system. So isothermal means the temperature is constant, isobaric means pressure is constant, and binary system means there are two components are present, that is A and B in this case. So according to his idea, molecular diffusion, the molar flux of species relative to an observer moving with molar average velocity is proportional to the concentration gradient in a certain direction. Now in this case, the molar flux of species means the molar flux of component A, and the concentration gradient is dCA by dZ. And in this concentration gradient, Z is there, it means it is in the Z direction. So as far as this Fick's prescription, JA is proportional to the dCA by dZ. So this proportionality is going to convert into equal sign with the help of some proportionality constant, that is DAB. So this D is diffusivity or diffusion coefficient, and with suffix AB it means the diffusion is occur from A to B. Now in this equation there is a negative sign which is related to the concentration gradient. So as A is going to diffuse, that is why the concentration of A is going to decrease with the direction in the Z or with respect to the Z distance. So it is indicated by the negative sign. So concentration gradient is negative, but the molar flux is positive. So this is the first law of diffusion equation, that is JA equal to minus DAB dCA by dZ. Now the JA is the molar flux of component A, DAB is the diffusivity, dCA by dZ is the concentration gradient. So if you observe the units of this DAB, that is meter square per second, then the units of this concentration gradient, now the concentration of Ca is kilomole per meter cube, then the unit of Z is meter, so this meter square, and from this meter cube meter square is cancelled, and now this unit becomes kilomole per meter square second. So this is the unit of JA, that is molar flux of component A. Now the diffusion occurs in the gases, in the liquids, and in the solids also. But now I am going to discuss about the molecular diffusion in the gases only. And there are two conditions where this molecular diffusion in gases is occur. So the first case is steady state equimolar counter diffusion. So this is the case where two components, that is A and B, are in equal number of moles of the gases and in the counter current conditions. So for these counter current conditions, this molar flux of component A and B becomes constant. So NB equal to minus NA or NA equal to minus NB is constant. And due to this condition, the equation Na plus Nb becomes 0. So for deriving the equation of molar flux, we must write the initial or the flux equation, that is Na equal to minus DAB into dCA by dZ plus Ca upon C into Na plus Nb. This is the basic equation for the derivation purpose. And as we know that the ideal gas law, that is PV equal to nRT, we can write PV equal to nRT, and from this equation we can write P by RT equal to N by V, and that is equal to C. So N means moles per volume, so that moles per volume becomes concentration. So we can write C equal to P upon RT. Similarly, for the component A, we can write Ca equal to PA upon RT. And in the derivative form, we can write dCA equal to dPA by RT. Now we can use these equations from this ideal gas law into this basic flux equation. So if you put this value of C here, if CA here and this dCA here, then we get the equation like this: Na equal to minus dAB upon dZ. So this dCA is going to replace by dPA by RT, plus now this CA is going to replace by PA by RT. Now this C is going to replace by P by RT and into Na plus NB. So this RT gets cancelled, and as this is the steady state equimolar counter diffusion, this Na plus NB equal to 0. So this bracket becomes 0, and this 0 into multiplied by anything is become 0. So the equation becomes Na equal to minus dAB dZ dPA by RT. So this is one of the equation where we can write this Na equal to minus dAB by dZ into dPA by RT. So we can integrate this equation by rearranging the parameters, like Na into integration dZ, that is limits from Z1 to Z2, equal to minus dAB upon RT integration dPA limits from PA1 to PA2. So in the next step, we can solve this integration, that is Na into integration of 1 dz, that is Z, and after applying the limits, that is upper limit minus lower limit, it becomes Z2 minus Z1, that is equal to minus dAB upon RT, and the integration 1 dPA means PA, and upper limit minus lower limit becomes PA2 minus PA1. Now as this Z2 minus Z1 is nothing but Z, and this minus sign multiplied to this bracket, so the equation becomes dAB upon RT PA1 minus PA2. Rearranging this equation, we can write dAB by RT Z into in bracket PA1 minus PA2. So this is the final equation for calculating the molar flux of component A as stationary coordinate in terms of partial pressures. So if the data is given in the molar concentration or molar fractions, then you have to replace this partial pressure in terms of concentration. And we know that PA and CA relationship, right? So this concentration, like generally C equal to P by RT. So likewise, we can replace this terminology and we can calculate the molar flux of component A. So this relationship of partial pressures or the concentrations or the molar fractions is shown in this diagram. So this is the concentration profile, that is PA, PB versus Z, that is distance. So this is one of the line that is representing PB1 to PB1 to PB1 condition, and then PA1 to PB2 condition. So from this line and nature of graph, we can understand the relationship between these partial pressures and the distances. Now the next case in the molecular diffusion in gases is steady state diffusion through a stagnant film, or the diffusion of component A in diffusion of non-diffusing component B. So in this case, the non-diffusing component is B and diffusing component is A. So again, to derive the equations for the molar flux of component A, we have to write the basic flux equation, that is Na equal to minus DAB dCA by dZ plus CA upon C into Na plus Nb. Now as it is a non-diffusing B case, so this Nb becomes 0, right? And we can replace this dCA in terms of dPA by RT minus DAB, and dCA is replaced by dPA by RT. Now this CA is going to replace by PA upon RT, and this C is going to replace by P by RT. So this relationship we have already discussed in the first case, and now only Na is there. So this RT gets cancelled and the equation becomes Na equal to minus DAB upon dZ dPA upon RT plus PA upon P into Na, right? So we can rearrange this equation, as here on the left hand side Na is there, and on the right hand side second parameter Na is also here. So I am writing this equation as Na minus PA by P Na equal to minus DAB dZ dPA by RT. So we can take Na as a common factor, Na in bracket 1 minus Pa upon P equal to minus dAb upon dz dPa upon RT, right? We can also write as P minus Pa upon P equal to right hand side same. Now by rearranging this equation for the integration purpose, we can write this equation as Na into dz equal to minus dAb upon RT. So these constant parameters are separated. Then dPa upon P minus Pa divided by P. Now it is multiplied by P, right? So we can integrate this equation from Z1 to Z2 and here from Pa1 to Pa2, right? So here on the right hand side, P is constant value. So P constant, dAb constant, R constant, T constant, and on the left hand side, Na is constant. So we can write Na integration of dz. 1 dz means z. So that is z2 minus z1 equal to minus dAb into P upon RT. Then the integration of dP upon P minus Pa. So that is in terms of ln, and minus Pa is there, that is why minus sign is also there. So minus ln of P minus Pa, and integration applies from Pa1 to Pa2, right? So we have to apply these upper and lower integration limits on the right hand side, and simultaneously we have to cancel this minus sign from this dAb and minus sign in this ln, right? So the equation becomes Na equal to dAb into P upon RT Z ln of P minus Pa2 upon P minus Pa1. So minus sign gets cancelled. Then we have applied the limits, that is Pa1 and Pa2, and from the left hand side the Z is carried on the right hand side denominator. So this is one of the equation, that is for the calculation of molar flux of component A of steady state diffusion through a stagnant gas film in terms of partial pressure, right? So this equation can also be written in terms of logarithmic mean of the partial pressures. So for that purpose, we must know the relationship between these partial pressures, total pressures, and what exactly the logarithmic mean means. So for that purpose, I'm going to write what the relationships are. So the logarithmic mean, that is for partial pressure, is PBM. So the equation for this is PB2 minus PB1 upon ln of PB2 upon PB1, right? So this is the basic equation. So if you write ln of PB2 upon PB1, then it becomes PB2 minus PB1 So this is simple rearrangement. But what is the relationship between P, PBA1, PA2, PB1 and PB2? So from the Dalton's law, we know that PA1 plus PB1 equal to P, or PA2 plus PB2 equal to P. So from that case, we can write this PB1 equal to P minus PA1 or P minus PA2 equal to PB2, right? So this is P minus PA1 and this is P minus PA2 from the Dalton's law. So this P minus PA1 can replace here and this P minus PA2 can replace here. So from this equation becomes N equal to DAB into P upon RT Z ln of, now this P minus PA2 is PB2 and this P minus PA1 is PB1. Right? So this ln of PB2 by PB1. Now if you observe this ln of PB2 by PB1 can be replaced here. So the relationship becomes like this. PB2 minus PB1 upon logarithmic pressure like this. Okay. So again, we can replace this PB2 minus PB1. So as you know that from here, if you observe, this is PA1, this is PB2. Now in this case here, PB2 minus PB1 is there. So PB2 means P minus PA1 and minus PB1. It means P minus PA1. So this PB2 minus PB1 becomes, now if you solve this bracket, then we get this P and minus P gets cancelled. So this is the PA2 minus PA2 and plus PA1. It means PA1 minus PA2, right? So this PB2 minus PB1 now becomes PA1 minus PA2. So we can replace here. Na equal to DAB P upon RT Z PA1 minus PA2 upon PBM. So this is the final equation for the calculation of molar flux of component A at stationary coordinates, where the steady state diffusion occurs through a stagnant gas film, or the diffusion of component A through the non-diffusing B. So this is the final equation for the second case. And this is the representation of this second case, that is diffusion of A through the non-diffusing component B. So on the x-axis distance is there, and on the y-axis P and PB are there. So you can observe the relationship between PA-PB and capital P, PA, PB with respect to the distances through this concentration profile. Thank you.